In the previous class, we have seen the truth table of a full adder and the K-map of sum for a full adder. In this video, we will see what is the output in the case of carry and how we can write the K-map, and based on the K-map, how we can draw the logic diagram. So earlier we have seen already the truth table of a full adder. So here, if we clearly see where ones are the output in the case of a carry, at which combination they are. If we see here, in this case, it is for 3. And the next case is 5. And the next combination case is 6. And the next combination case is 7. So, if we write these ones at that particular places in the K-map, this forms the K-map for carry. So, here this is an independent one, 1, 3, 5, 6 and 7. We are having ones. So, here if you clearly observe, we are having adjacent ones. This one is adjacent to this one and this one is adjacent to this one. This one is adjacent to this one and this one is adjacent to this one. All are adjacent to each other. So, we know clearly that if we have adjacent ones in that fashion, then we can create a combination of these two and combination of these two and combination of these two. We can only map adjacent ones only. We can, you can clearly see in the K-map tutorial that is available. So here I have mapped these two. So these two are having the same similar expression as AB only. But here the third variable Ci dash and Ci varies. So these two are complement to each other and these two gets cancelled. So only this AB remains. Only these two input values remains. That's why for these two one combination, I have written the output as AB only, as these two got cancelled with each other. Coming to the next combination, this is another combination 1 and 1. So in this case, these two are having the common variable as Ci and these two are having the common variable as B in this case. And A and A bar gets cancelled here as these two are complement to each other. So the entire expression becomes, for these two combinations, it becomes BCI. And the next one, the third combination is Ci variable is common in this case. So here you are, if you clearly observe, these two are complement to each other. So these two gets cancelled and A remains. So the total expression for carry is ACI in this case, in this combination, for this combination. So the entire expression for the three combinations is AB, BCI and ACI. So we will be reducing the K-map in such a format. So the final expressions for K-map for sum and carry for a full adder is given by A exclusive or B exclusive or C, and for carry AB plus BC plus AC. So if you clearly see here, we can implement the sum using two XOR gates. And here, this is nothing but a sum of products form. AB product is added to BCI product is added to ACI product, which will result in carry truth table. So this is the logic diagram for sum. So here I have considered two XOR gates where A, B are given to one XOR gate which will perform one XOR operation, A exclusive or B. And the output of this XOR gate, A exclusive or B, is fed to another XOR gate where another output of this XOR gate is given to C. So we have included all these three variables using two XOR gates. In the case of half adder, we have used only one XOR gate which adds only 2 bits at a time and gives A exclusive or B as sum. But here we already know a full adder adds 3 bits at a time. So C is also considered in this case, and we are adding it with another half adder in this case. So this is first half adder and this is second half adder. As we have already seen in the first video lecture, how we can implement using a full adder using 2 half adders. So here C is given to another half adder. So the resulting output is A exclusive or B exclusive or C, which is equivalent to the sum that is derived from K map. So ultimately the sum is solved. Now for carry, the logic diagram for carry is given by AB plus BCI plus ACI. So we have used 3 AND gates here, which gives the product of the 2 given input signals, AB, here in this case BCI, and again in this case ACI. So we have added here these 2 terms, AB and BCI, using a OR gate, and again this is fed to another OR gate as an input, which results in carry output. So the output here is AB, BCI and ACI. So whatever the output we are getting here is equivalent to the output that we have derived from the K-map expression. So the entire logic diagram using the gates what we have designed is this one, which includes 2 half adders, A exclusive or B and A exclusive or B exclusive or C. So here we can see that there are 3 AND gates which are here. Now I want to give you an assessment how we can reduce these 3 AND gates to only 2 AND gates, and how we can reduce the number of gates in this carry section. This is an assessment or example that is given to you as an assignment to solve reducing these gates using any mathematical procedure, so that we can reduce such a fashion gate. This is also a full adder, how we can reduce it and derive it mathematically. This ends the video lecture here. Thank you for listening.